just did is, I mean, we saw yesterday that these two are interchanged, but do some straightforward mathematics. Okay, if you want to cheat a bit, then you look in this Gunther Wolff write-up, and what you will find there is something that the scattered electron energy in the end is a quantity which is 1 minus y. So yes, we calculated that, which is very handy. It is the electron beam energy plus x times y times the proton energy in the end. Okay, maybe such an equation is relatively intuitive in the end, and we can do the numerics on it. So here we have a factor of 0.9. This was 27.5 GeV. Then beyond that, what do we have? We have an x value of 10 minus 3, right? That was given over there. We have again this y value, which is 0.1, and then we have an energy of about 920 GeV. Okay, so here also the numerics are not that hard in the end, right? I mean, this is about 25 GeV. In the end, it's a 10% reduction. If you wish, this is 10 to minus 4 times 920. So that's about 1 in the end. And indeed, if you do this a little bit more precise, if I did it right, you end up with the scattered electron energy, which is about 24.8 GeV. Okay, so it's calculable in the end. It's a little bit lower. What you can also do is look up the same expression for cosine theta scattered angle. And I do have these also in the slides later on, right? So if you just want to follow along and find out where I make the mistakes, go ahead. So if you look this up, or if you go through the math, and it's certainly worthwhile to do that at some point for yourself, you will find that, of course, this cosine theta E prime is a ratio in the end. So this is a square bracket here, or at least my impersonation of it, times an electron energy. So you always have a combination of a proton and an electron energy, and then you divide it by, I'm going to send it your way, I'm sorry about that. Going to do that like this. Again, something like x times y times your proton energy in this case. And instead of the minus sign, you have a plus sign of 1 minus y times this electron energy. So again, you can do the numerics here. Right, I mean, this sort of value, x times y times the proton energy, well, that's the 10 minus 3 times the 10 minus 1 again. So it's a fairly small number in the end, times the 920, that makes it a little bit bigger. Then here you have about 0.9 times 27.5, so that ends up again with this value of about 25. Here you end up with that same value. Here you have the plus sign. You have a plus sign and a minus sign. You end up with, let's say, a small perturbation on your 25, which is the leading term in that. So what you sense is that this ratio will live close to 1 in the end, but not quite be 1. And if you work that then through this one, you end up with a scattered electron energy, which I think is at the level of about 173 degrees. Okay, so it's close to minus 1, right, because of this minus sign over there. So it's an angle which is rather large. What does it mean that this angle is rather large? Well, given that this electron came in from the left, had a minus sign up front, it actually means that you have relatively forward scattering, so scattering into your end gap. Okay. You can ask another question, which I think was on the slide before Alexei took it off. Clearly did not tend to calculate, that was obvious.
He was trying to do better.
Oh, okay.
Yeah.
All good, right? That was this struck quark, right? So if you go through that exercise, there's a similar expression. What you end up with is an angle which is about 120 degrees. 120 degrees is about mid rapidity, right? We had also decided that the equivalent energy was something like a 25 TeV electron beam. So in a fixed target experiment, if you would do this experiment, where would this struck quark go? The only place it can go, very, very forward. So what you get from your collider is not only a center of mass energy that well exceeds anything you might be able to do as an experimentalist in a lab. You also get from it actually a fundamentally different topology into your detector. You're not longer in the midst of, let's say, remnant quarks. You're clearly separated. You've all of a sudden separated your current jet and your target jet. That's one of the key features of a collider and one of the key benefits. And of course, you need to instrument for that. It's also one of the reasons why, if you want to make semi-inclusive deep and elastic scattering measurements, you actually need to have a wide acceptance collider detector. Okay, and that, I think, is kind of the benefit of making some of these calculations, if you wish.
Why is that called? Oh, is it minus 173?
No, it's 173.
So sorry, I'm getting forward and backward mixed up. So did it come back towards what
It
did
scatters in the, it continues along its path,
Thank you.
essentially.
When people talk about a rapidity gap, what do they mean?
An opening in collision products.
Right.
Right, so I would not use that in this case. And I would associate that more with diffractive processes. I would typically do that with respect to the remnant. That hopefully stays intact in many cases. That I possibly, as a matter of taste, think is one of the more interesting pieces of EIC physics. But there you could use it, indeed. And then if indeed this proton still breaks up, that's I think the common way of using it. I've not really seen it to talk about differences between scattered lepton and let's say your current jet. Okay, there's no reason. I mean, it is a gap. It seems proper English, but I've not seen it that way. So this is all calculable, right? And it's useful, if not a little bit tedious, to just once in a while do that. See if I not. So we did this at this point, right? Let's now move away from having to do every single tedious calculation ourselves. Thank you, Alexei. And let's have a look at some simulations, right? But in principle, one could calculate all of that rather easily. So what do we have here, right? I mean, here, I use my analog pointer, learning from yesterday. Let's say we are very interested in even the non-perturbative parts of, so q squared smaller than 1, smallest possible x. Okay, where would scattered electron end up? Well, it would end up incredibly forward. Logical, right? I mean, it's almost a fixed target experiment in that case. Now, stepping this forward a little bit, so a region here, much more modest values of x, but very low q squared. Scattered electron is still rather forward in the end. It's just a feature. I don't have a very rapid moving target of which I'm scattering in the end. Moving up a little bit, what do you see happening? So now we are getting close to this region actually, well, we calculated for here energies, but 10 minus 3 and q squared of 10, right? I mean, that's more or less this, this thing here. Here we are. You've opened up a little bit in your phase space in the end. So what we have seen now by doing this is going backwards, right? I mean, very forward scattering, you open up your kinematics a little bit, you open it further a little bit. does not seem to go very rapidly. These are still pretty small angles in the end with respect to this beamline that lives over there, right? Step it further. So now let's move into what is almost a valence region, right? X10 minus 1. But look at that for a bit higher Q squared, so somewhere like 20 or 30 GeV. You see actually that you open up further and further. But you don't open up all the way in the end. Then stepping to an extreme, right? I mean, look, highest values of Q squared, that's of course attractive, right? I mean, W's or Z's might be exchanged there in the process. Well, not if you measure a scattered electron, then it could be a Z, but not a W. And what you see actually is that, well, you start to indeed come out pretty far in your angular figure. I mean, again, these are simulations in the end, right? I mean, so you have formal distribution, you also have a finite range in it. The hot spots are, of course, in red, and then it falls down to the cool spots, which are in blue. Okay, now, what that means in the end, and it's completely logical from a DIS diagram, at least the leading order one, that the kinematics X and Q squared is completely determined by the scattered electron. The reverse is also true. Namely, you can get from X and Q squared, of course, the scattered electron energy, as we've just done there. These are just the inverse relations for it. It's illustrative to see as well that even in these sort of laboratory quantities at this point, you still have this 1 over y dependence. So in the end, what that means is experimentally, if y is small, it's probably a difficult measurement to make, in that small changes get amplified rather a lot. Now, scattered electrons, that's all fine, right? But we have 2 or 3 orders of magnitude in luminosity. It's certainly worthwhile to look at the hadrons that are solid produced, or look at the current jet and see what those objects actually truly do. You see here is the distribution of negatively charged hadrons for 15 on 250 GeV collisions. 15 GeV refers to the electron energy. And what you see are the distributions for different angular ranges, now expressed as pseudo-rapidities in the end. Okay, so electron direction over here. See, of course, a clear peak, right? I mean, cross-section will be large when nothing happens. And then this very hadron hemisphere, where just nothing, electrons will not be scattered there to a large extent. What you also see is that the number of hadrons compared to the number of electrons is not some sort of constant or so. I mean, again, these are logarithmic axes vertically as well as horizontally. So you have regions of the phase space where you just have to accept that, well, I mean, take something here, that your hadron background, if you're interested in electron, can be orders of magnitude larger than your electron signal. So in other words, what that means is that you better think about your particle identification subsystems. Okay, it's probably multiple in that case. The last thing which is probably quite visible in the end is that if you look at this horizontal axis, that you actually see that there is quite strong correlation between pseudo-rapidity and momentum overall, right? So clearly, I mean, here you start to see in terms of the hadrons that is a very, very different distribution, for example, than the distribution over here. Yeah. And okay, note also that if you extend that further, and that of course drives this correlation to its extreme, that the range of the axis here is actually different, right? I mean, this extends out all the way to the hadron beam energy, of course. Okay, this 1 over y matter, that's a little troublesome, and we'll see it illustrated in a different way later. But think about this DIS diagram again, right? I mean, if this is indeed something as simple as indeed this incoming electron, scattered electron, and here you have some form of proton, you pull out a quark that then goes somewhere, and you have a bunch of spectators here. I mean, of course, this scattering point there, the kinematics of this collision, so something like Q squared, can be constructed from here, can also be constructed from here in the end. So you have multiple means of going at this in the end, and those have been worked out at HERA. First off, you could look at, of course, the electron. We've done that, right? So this is called this electron method. Well, okay, I mean, you can calculate what y is in terms of your observables in the end. You could also go entirely from hadronic observables. That is known as the hadron method, or Jacket-Blondel, after the people who came up with that early on. So what you do in that case is you look at all hadrons in your experiment. In the end, you sum in this sense, right? I mean, so the difference of the longitudinal component of momentum and the energy, sum that, you get your sigma term. You likewise compute what this T term is, which is something like, think of it as a PT, which is essentially what it is. And what you get at that point is rather straightforwardly. First off, that your Y value is the sigma divided by the electron energy. So that's a quantity that has not depended at all on the scattered electron itself, because this is beam energy. And your Q squared value, I mean, you can reconstruct indeed again purely from hadronic observables, say. Okay, and of course, likewise, I mean, if you know Y and Q squared, you know X, right? Given that you know the center of mass energy. So what's the advantage? Suppose that for whatever reason you have a gap in your electron capabilities, you're not dead in the water, provided that indeed you look at the hadronic final state. Of course, there are mixes of that. There's also a method that actually tries to avoid any form of energy in the problem, which experimentally is quite nice, because that means that you don't need to worry so much about absolute energy calibrations, for example, which is tedious with a calorimeter. That's known as this double angle method in the end. So that is mostly built out of angles, as you can see here, right? I mean, this clearly is also an angle in one form or the other. And now you can say, well, okay, but if you compute that from something like this, do you still have an energy in it? Yeah, of course you do have an energy, but that's is a different beast. That's very different from a single particle. So you can ask yourself, like, well, okay, so these are just 4 methods, and maybe we should go at that at some point with full kinematic construction. Maybe this is an item for machine learning, actually, right? Why not? Why would you not throw machine learning at looking at a picture of a collision and ask what the kinematics are? Doable nowadays, maybe not at the time. At the time, people started with math, but you can ask the question, where does it work in the end? So what is here? Again, from the standard work on that topic, okay, what you see is for different methods, 4 of them is labeled at the top, for different Y values, the X value as it's reconstructed divided by the X value which it really was supposed to be. Right, so what you get to see is asymmetries in your distribution as well as biases, right? So a distribution like the one in the corner here is clearly living in its average below 1. That's a clear bias, and it's furthermore an asymmetric thing. So this is really not the type of reconstruction you would want to make if afterwards you're going to tell your theory friends, well, the uncertainty here was something, and they say, oh, that must have been Gaussian, right? I mean, clearly it wasn't. On the flip side, of course, you see that this electron method works fantastically well at very high values of Y. This also means that in your experiment, you can trade off, right? You can study even the correlation between these methods and combine them if that is what you would want to do. Now, qualitatively, outcomes of that, what you can see is that clearly in a case like this, relatively low Y, you start to see that this electron method has broken down effectively, right? I mean, it's sort of here. It's actually such that this method based on hadronic reconstruction performs better, at least from a resolution point of view. Okay, it has a bias to it. In this case, how it was studied, but perhaps that's correctable. So these type of trade-offs, they are worthwhile, and they only come about from different ways of looking at the kinematics in the end. And then this double angle method is maybe unsurprisingly something that works remarkably well for these highest Q-squared events, where energies are particularly high. Okay.
Can I ask a question?
Yes, please.
I just wanted to know if it's necessary to kind of like first look at all the methods, electron here, and at same Y values before maybe probe these different Y values. Is that necessary?
I'm not sure I understand your question.
Yeah, because here maybe you're missing some content here, because here we're looking at different values for these different methods.
Yes.
Yeah, shouldn't we like we need to measure the performance of each of the methods by first pick one Y value for all the methods out there before.
Yeah, I see what you mean.
Yeah.
Thanks for clarifying that. Yeah, that's a fair question, of course, right? I mean, you do not upfront know what your Y value is. You have to construct it from an actual experiment. The typical way you would go about that is by comparing your Monte Carlo simulation with your data. If you have agreement, then the typical experimental approach is to say that you understand what your experiment is about. Okay? For writing an article, this of course works fantastically well. It's a classification. Thanks for the question. Okay, now to kinematic planes again, right? I mean, now just let's calculate this through again in terms of this scattered electron. You see it at the top here, and this actually is for EIC kinematics, so 20 GeV on 250 GeV. Okay. So what do you see? Lines in red are isolines of scattered electron energy. So what do we see here? We see an Atari-like figure, right? With a dividing line that seems to live here on or about 10-1, a little bit below. Namely the ratio of the electron energy divided by the proton beam energy. You also see is that here, this one isoline that sort of lives at the bottom, the scattered electron energy is 18 GeV, whereas here, at the very top, it's 22 GeV. In other words, if I make a measurement of the electron energy that is 20 GeV, but my uncertainty is 10% at the spot of 20 GeV, I'm actually not able to resolve Bjorken X at all with any confidence. Okay, it could be all over the map in the end. So that's the nastiness about such Atari figures. They have large sweeps. How does that come about? Well, it comes about because isolines of Y actually move up like that. And this is an isoline where Y equals 0.01. Okay, so purely from an electron method, as we have seen from this previous page, I mean, this sort of region, it's just hard to measure with electrons only. Okay, so much for the red stuff, right? I mean, you could do that in blue as well. That's indeed pseudo-rapidity. So that is, if you place your detector at one particular angle, what sort of energies is it going to encounter? So you can pick, for example, the pseudo-rapidity of -3, right, which would live somewhere over here in the end. So it's clearly in the lepton end cap. If I walk along this line, what sort of isolines in energy am I going to encounter? Well, I'm going to encounter 18 GeV and lower values. Okay, so in this hemisphere, what you will see is that essentially everything lives below the scattered, below the electron beam energy. I could do something entirely different. I could move myself into, let's say, big mid rapidity. Okay, so over here, we had seen that there is a cross section for a scattered electron. If we do that over there, then, well, this is this line of eta equals 0. What will you encounter? You will encounter anything between 0, the lowest possible value, so your threshold, up to at least the very high energies, where the scattered electron energy is actually larger than the incoming electron energy because it has picked up energy from the proton beam. These events are rare. Okay, that's quite clear. This is super high Q squared. Cross sections drop off as 1 over Q to the 4th, at least. but it's not impossible. Okay, that was one of those funny things yesterday that I think have confused more than a few. You can indeed, in a collider, end up with a scattered particle that has a higher energy than the energy you put in. It's just a transfer from the other beam. Nothing more or less than that. Okay, now you could look at that struck quark, right? I mean, so here you see the equivalent of that figure. Again, in this case, these quark energies, as they ramp up, and the isolines of pseudo rapidity in this case run like this. There is actually a symmetry between these two figures. You can work that out mathematically. That's tedious, but it's illustrated too. And in principle, we could check whether the math I did there is more or less correct. What you get from that, again, is also that you have this crossover that lives at this ratio of these energies. And in this case, in terms of your measurement, you would only be concerned at very high values of y. The low values of y, you see here an almost linear dependence and increase. Okay, that also goes very directly at that if you're interested in low value y measurements, just look at this figure. I don't have a vast sweep in Björk and X if I start from these observables here, but I do have it over here. So in other words, what I'm seeing here is just that an electron method in that case is inferior to a hadron method. Something you can just read off from isoline figures in here. Okay, now any experiment you build will of course cover not all of the phase space. That never works. Cables need to go somewhere. So trade-offs you make in that exist. And they can express matters of preference if you wish. You should be smart about it. Now, a thing that is often overlooked, but I think it's again one of those very simple considerations that actually really matters for your experiment design, that is the question, what is your rate environment? But we had seen that these cross-sections sort of go as 1 over q to the 4th. That means as q squared is very small, that is where the cross-sections are largest. That's what drives the physics rate in the end, in such an experiment. Well, okay, what is q squared equals 0 or something close to that? That's photo production. Photo production cross-sections have been measured over very, very wide ranges. The units, okay, I mean, that's a topic for discussion in the evening. Whoever came up with the idea that you should call a cross-section a barn, I don't know. I mean, yeah, I don't know. I mean, maybe there was a bar in that barn or something. Cross-section is at the level of 0.1 millibarn. As you can see, it's essentially constant, right, with square root of S or with your laboratory frame, if you wish. So photo production is the dominant cross-section. It's rather well known. I mean, this is essentially an interpolation in the EIC range. It's also about 2 orders of magnitude below cross-sections at RIG, EP collider, and the LHC. And if you compare this with, let's say, luminosity projections of 10 to the 33rd or 10 to the 34th, where of course we now take a normal unit like centimeters per centimeter square per second, that implies actually a collision rate, a physics collision rate that is at the level of 50 to 500 kilohertz. That's not very large by modern standards. I mean, that actually is what current experiments reach in terms of their trigger rate. Even. So that's actually in a way very, very exciting. Okay. That also means that sort of the time between collisions is at the microsecond level, which means that you should not upfront reject use of a drift-like device or a device that is a little bit slower, if that gives you other benefits. Okay, because you're still dealing with a single collision within that window of that drift in the end. It is of course true that this is much, much smaller than the bunch crossing rate at the EIC. So that also means that most of the bunch crossings actually don't result in a physics collision. The situation is very different in the hadron colliders, where it's typically more than 1 collision per bunch crossing. And of course, look, truth in advertising at an EIC background rates could be larger, right? I mean, this was about the physics rate environment. This says nothing about a potential background rate environment, ill-defined or ill conceived experiments where, let's say, you would be bending the electron beam inside the experiment, certainly result in large Bremsstrahlung components contributions. Further thing that's just a simple extension. Of course, over the years, also many compilations have been made event multiplicities per physics event. The ND eta at RIC was a hot topic 20 years ago. Okay, I mean, before that, it was a hot topic, of course, in any other collision system because we didn't know it. Those rates, if you want to think about them as rates, they are handfuls. So think in terms of 10-ish particles or so being produced per collision. So these collisions are relatively low rates and they produce relatively few particles. They're relatively clean in the end. That has actually very interesting implications. If you look at a figure like this, this is very experimental in a way. So it's at the startup of the LHC. And what does it aim to do? Aims to map out where the frontier is in terms of event size of an experiment on the one hand, and call it trigger rate at some level, usually levels in experiments, on the other axis. If you plot your different experiments, of course, you will find that there is some form of frontier in that, and that there are simpler experiments. Already at that time, if you look at this frontier, I mean, 10 to the 5th in terms of an event size. I mean, that is sort of what Hera and H1, so Zeus and H1 had. Their rates were rather low. Now, if you bump this up by an order or two in magnitude, you're still below the trigger rate of LHCb in 2012. Now you can say, okay, so EIC is not at the forefront of, let's say, the rate envelope or the data volume envelope. Yeah, it will not be. Is that a disappointment? Well, okay, I mean, if that's what you're after, it's a disappointment. But in practice, what does it actually really mean? It means that the challenges of pumping away the data, at least technologically, have been solved already at the LHC. And furthermore, that you may find yourself in an environment where for once you're not limited by your Monte Carlo samples, for example. In other words, it's very timely to think about very new and different ways of data analysis. You will not likely be limited by your compute environment. Now, that's also a bit of a shocker. I mean, to me, it's a shocker. Okay, because, well, when I sit behind my laptop, right, and I go like, oh, okay, I notice immediately that I'm anyway not limited by the laptop, I'm limited by myself. So take it as a challenge, okay? I think it is time for really new analysis paradigms, and the EIC may well bring us there, given that the rate and the event size capabilities have essentially been met already today, and we have almost a decade of compute advancement to go. And that's a really exciting prospect, actually, in a way. That's also why I started imagining yesterday that you could think about EIC. Maybe it is such that if you turn this on, that you indeed have, like a microscope, a real-time picture of a TMD distribution. How wonderful would that be? Okay. Okay. So detector requirements, maybe, right? So the theorist perspective. The experimentalist thinks that the theorists think about detector requirements as simple as, well, you need to detect all final state particles, of course. Okay, we want to ensure exclusivity. I mean, you need to positively identify them, right? I mean, if they're kaons, you need to know that they're kaons. You need to measure the form momenta, preferably also the time, right? 5D tracking, getting there too. And uncertainties, what do you mean by uncertainties in the end? So that's not quite how it works in the end for an experimentalist.
I want to ask the question on that. In the theorist's mind of detecting all final particles, but usually there's also new physics involved, whereby new particles are produced and you're completely not aware. So in such situations, how do theorists and experimentalists come together and agree?
As an experimentalist, I would ask, what is the bracket on this? Okay, so what is the largest cross-section you can come up with, and what is the smallest cross-section you can come up with? And I would find out whether that's within the capabilities of my instrument. And if the problem is interesting enough, then you change your instrument so as to satisfy that bracket.
Whether it's inclusive or exclusive.
Sure. I mean, look, I was not directly involved with this myself, but if you take the LHC, where the goal was to discover the Higgs, what was the optimization? The optimization was to achieve 5 sigma over a vast range in energy. One went at that with the biggest possible hammer. Okay, I mean, that may not be practical for EIC purposes. I mean, you don't have a 5 sigma make or break goal, I would say, but that is more or less the path I would take. Okay, look, so experiment, right? I mean, experiment is first of all that the particles, yeah, there are many of them, but most of them are not so stable in the end. So most of them just decay in one form or the other. So that means that you need to come up with indirect reconstruction methods, be it displaced vertices that you need to measure, invariant masses, missing energies, could be all sorts of things in the end, full kinematic reconstructions. Again, I think an area where machine learning might make a difference. In the end, then acceptances, I mean, look, there's beam pipe and other pesky details that never get it truly complete, of course. Typically, instruments need to be coupled to electronics. That comes with its own slew of issues. You need to optimize the limitations of algorithms, you name it, right? So life is never that ideal. And furthermore, these non-ideal instances all require extensive study typically, and many trade-offs, typically between purities and efficiencies. Now, particle identification, that's of course a likelihood problem as opposed to a certainty. And you can go on and on and on. And indeed, backgrounds, yeah, those too. But quite often, those are highly unknown, actually. So there is now the 884-page version of the collective community wisdom on science requirement and detector concepts. Okay. I would say deal with that indeed as a encyclopedia rather than something to be read from beginning to end. But there are nuggets in there of real gold, I would argue. Let me try to condense this a little bit with some of the things that I certainly picked up on myself. The first message out of this is that the experiment you design needs to be a wide acceptance. Okay, so where we saw that the dominant part of the electrons were sort of confined to, let's say, 2/3 of the full angular range, they don't make it all the way back typically to the hadron arm. Hadrons certainly do that. So you need to make an experiment that is very wide, in particular if you want to make semi-inclusive measurements or any form of correlation measurements. You should strive to be hermetic. You should strive to have a very low inner material budget, so as to minimally perturb any particles that are produced before you actually detect them in the end. Vertexing capabilities will need to be at the level of 10 micrometers in the end, so that's rather small. That has to do with the energies of the particles you produce. We discussed yesterday evening C tau-like quantities. These are the needs. Charged particle tracking is actually challenging, in particular in the lepton end cap for the scattered electron. It becomes very challenging, if not impossible to meet, actually. So again, that goes at very low material, big challenge to do. Of course, if you find that you have a challenge in one area, then your instrument demands on your additional subsystems go up. So indeed, you need to have an exquisite electromagnetic calorimeter in this lepton end cap. That's how life goes. Matters will come out of combined analysis in the end. Then hadronic calorimeter resolution, that's kind of straightforward. A new and unique feature, certainly also new and unique compared to HERA, is that you need excellent PID capabilities. And you need those PID capabilities over a very, very wide range in energy. That goes quite directly at, I would say, passage of particles through matter. That's why I inserted this initial reference. You cannot have bending of the electron beam inside the detector in view of backgrounds. And yeah, you could ask the question, you've said nothing about the magnetic field. Magnetic field that is currently being considered for the detectors at the EIC is about 1.7 Tesla. You could ask a question, well, so why actually do you do this with magnetic fields? In many atomic physics experiments in the end use electric fields. Why is that not used in high energy physics? It's a fair question for the evening, I think. Could be a fun discussion. Also, of course, as an experimentalist, you again look back, what did HERA do? Yes, it was limited in, for example, its luminosity capabilities. But hey, 30 years of CTEQ development, maybe that is not the area that I should be too worried about. So there were two experiments there, Zeus and H1, and they ended up being complementary to one another, and that was over their capabilities. So Zeus has probably the best colorimeter ever built for high energy physics experiment. It was depleted uranium, it's compensated, ideal. Magnetic field actually is 1.4 Tesla. In the case of H1, the design is probably more of a collider detector, a bit more general purpose. It certainly also in part of the running period actually had better diffractive capabilities. There the magnetic field was 1.2 Tesla. So for the EIC 1.7 Tesla, is that conservatism? Is that thought through very carefully? I think that debate is actually open. It's one of the most difficult things to do right in an experiment, and it's also one of the most permanent things you do in an experiment. Typically, when an experiment gets upgraded, it's not the magnet that gets upgraded. Once a magnet gets upgraded, it's essentially a new experiment. So for the project detector, how did that go at the EIC so far? So there have been proposals. There have been 3 proposals submitted to an advisory panel. So 3 proposals submitted, 3 proposals reviewed. The outcome of that was that the committee felt that 2 of these concepts could satisfy what are identified as the core science goals. And then it selected one of the 2 concepts that could do this. And this has been adopted by the project in the end, so that serves as a reference. That doesn't mean that you start to build. That means that you start to do additional work to actually optimize your detector. But you start from a starting point, which is, well, is ETCH reference. So it's a 1.7 Tesla solenoidal magnetic field. At this point, that's actually already different from ETCH, and other optimizations are ongoing.
What were the fields for core and Athena?
Yeah, so core, so maybe an additional word. Athena was a launch for 3 Tesla solenoidal magnetic fields. And so it has 2 aspects to it. One aspect is that the field strength is larger. The second aspect is that the radius is larger than the ETCH design. Core took the exact opposite approach. It's also a 3 Tesla solenoid, but it actually tried to keep the radius as small as possible. Okay, so between the 2, you probably have spanned a certain space of a certain part of the parameter space.
And was it core that didn't meet which are the 2 that met the science requirements minimum?
Athena and ETCH.
I'm just curious, is it because core was too small for that big old?
I don't think that let me put it this way, that's not how I would characterize it. I think an aspect that actually went into that also goes at the strength of a collaboration. And the core collaboration was a small group of very dedicated individuals. Within the available time, they got only so far. And that probably set them back a little bit compared to the other experiment proposals that were each individually bigger And as an outcome of actually this selection, if you wish, it's of course a merger. Right? I mean, there was also the acknowledgement that neither this collaboration nor that collaboration could build the instrument starting from that day. They lacked certain expertise, etc., and people. And so even set aside from pure financial resources, it's even a human power question. Okay, particle detection 101, right? I don't want to turn this at all into, let's say, a technology review. That's not the goal. You could easily fill another hour with that if that's what you want to do. But I do want to give you a little bit of a sense. First of all, that short-lived particles are usually detected through their long-lived products. Now, luckily, there's something like 200 or so particles in the particle data booklets. About 10 or 15 are long-lived. So it's something that you can count on fingers of two hands, toes of a foot. So that's something you could classify in the end. Usually they're detected through their interactions with matter in the detector itself. That's maybe kind of obvious, or let's say in combination with their interactions in fields. Now these interactions, they typically produce light of some sort, or let's say another form of electromagnetic radiation. And in one form or the other, you then need to translate that into a signal you can record, which is typically an electrical signal. So the standard device for that I think is in every textbook by now, is actually a remarkable piece of creativity, namely the photomultiplier. Right? I mean, you knock out an electron from a metallized piece of glass. Typically, you enter some sort of vacuum where you guide yourself into an increasing strength electric field. And as you knock out electrons from these plates, your signal amplifies. Who comes up with this sort of thing in the end? I mean, yeah, of course, if you've read the textbook, then you come up with it. But before the textbook, it's just astounding what people go through. Okay, and even though this may be the most boring example nowadays, you should be cognizant that as soon as you stick this in a magnetic field, it doesn't work very well. And guess what? We now have silicon photomultipliers, right? I mean, that's basically 70 years or something like that removed, and 70 years of advances, and they still don't work particularly well in magnetic fields, at least not very high magnetic fields. Okay, up to 2 Tesla or so, it's doable. Beyond that, you need to optimize. So if you think that this is trivial, here's an opportunity. Go and fix that. Okay, and you'll find that this is not for the ones that have short attention spans. So the physics is often very well known, right? I mean, it's completely obvious what happens if you put a magnetic field in one direction or another on top of this. I mean, of course, this sort of focusing is perturbed. Completely obvious. Now, putting this up in a robust way, that's a different matter. The applications, I am just always surprised and actually just amazed by the creativity of people once they have a goal. Okay. And what they do, they spend decades of their time and life to create new capability. So it requires persistence and typically also a lot of focus. The new capability, though, pays off. I mean, we've seen that, for example, with polarized electron sources before. It's likely. So another example of just a stunning piece of instrumentation with remarkable creativity is a time projection chamber. Does anyone have an idea work on such a device at this point? Know how it works? Want to comment?
Time projection chamber, big gas cylinder filled with typically noble gas, plus, let's say, methane, but I'm not sure if you want to go into details why the methane is there. But point is, charged particle goes through, excites, kicks out electrons from the noble gas, and we apply electric field. So we collect the electrons on the end caps, on the end sides of the TPC. There the signal gets amplified, similar to the PMTs, and we collect the charge at the end caps. And typically, let's say PC star TPC also provides timing information, so we know where the electrons came from within the volume of the TPC. So we get 3D information where the charge passed through the TPC. And also how much energy it lost inside the TPC. So we apply the magnetic field we talked about, we get the curvature, so we get momentum. And based on how many charges were created, we get the energy loss. So we can do PID based on energy loss.
Instead of the old with overheated vapor, the magnetic field where you have trace this spiral traces of particles.
Yeah.
Thank you.
Yeah, now we will get maybe better explanation with graphical.
This is more or less what you described, right? I mean, this is your particle track that in one form or the other curves in this magnetic field. You have an electric field that then drives the ionization to the end caps, where you have a plane that reads this out, often with an amplitude, as well as its timing information. Right, and that allows you to report in the end the time projection, and the amplitude gives you the size of the energy loss, and the energy loss is related to the particle time. What an amazing device, right? A large volume, small area where you read out. Who comes up with this? Okay. And well, then if you see the scale here, I mean, you can see some heads. Here, for example, right? I mean, here's the top half of a person. And this is a 4-meter device in the end. So people go through amazing levels of innovation and construction to actually achieve quite fundamental goals in science. And indeed, exactly as you said, thanks so much. Right? I mean, you are able to measure this amplitude, and that means that this device not only serves tracking, potentially vertexing, so position measurements, but in addition to that, forms of particle identification that actually work pretty well up to, let's say, about a GeV or so in the case of proton, pion, and kaon separation. It's nothing to sneeze at. It's quite important. Now, okay, last example of something that I'm just completely astounded by. That's the developments in silicon at this point. What you see on the left-hand side is a vastly blown up single pixel of ALICE ITS2 silicon sensor. And within a thickness about 50 micrometers, you actually have your volume where you produce your electrons, you have your collection of your electrons, and you have the electronics to drive it out. All of that in 50 micrometers of silicon. 50 micrometers of silicon corresponds to a radiation length of 0.05%. At this point, our ALICE colleagues are actually heavily pursuing implementing such a detector without any form of additional mechanical support. This is the closest we can get at this point to having a detector with nothing in its interior. I mean, how creative and beautiful is that? Okay, so a couple of examples, right? I mean, just to list it, I think it is useful for some particles to know at least roughly what you're dealing with, right? I mean, so this simple table in the end. Take B mesons and D mesons, they decay weakly. I think it came up as a discussion topic also yesterday evening. The way you would go experimentally about that is through a form of topological reconstruction over a secondary vertex. Of course, if you pick another example, right, I mean, look, take muons in the end. Of course, the dominant energy transfer mechanism is ionization. And typically you end up with a track that goes through your entire detector and then escapes. That's how you would look at it. It even traverses your calorimeter. So this is a table just for reference if you have not seen that before. Detection, then typically we still separate in terms of tracking, particle identification, calorimetry. Spend too much time on this in the end. That classification is a little bit artificial, as you've seen from this example of the time projection chamber. Likewise, calorimeters are segmented, so they do provide a form of position information. Still useful to be able to discuss with your colleagues. And the typical, I would say, distinguishing characteristic is, of course, that calorimeters aim to measure the total energy, and they do that by stopping a particle in essentially all cases. that stopping of that particle can go over electromagnetic interactions and hadronic interactions. Of course, both of these processes have a characteristic scale associated with it. Well, we can do a vote. Who thinks that the electromagnetic radiation length is longer than the hadronic radiation length? Nuclear interaction length, if you wish. Well, nobody. That's great. We're all ready to design our experiment with the hadronic calorimeter on the outside layer. That's exactly what I want to do. And that's precisely why you get to this sort of nutshell cartoon, an onion of experiments. This is often referred to as the onion of an experiment, right? I mean, everybody thinks about the layers, right? As in, okay, I mean, if you peel from the outside in, the outermost one is your muon detector, then you have your hadronic calorimeter, typically your magnet, your electromagnetic calorimeter, because you want to get better resolution out of it, PID tracking, and then, well, your vertex trackers. That's not why it's called an onion, okay? It's called an onion because the integration challenges here make you cry. Okay, that's the reason why this is called an onion in the end. It's typically the integration that makes it so hard to actually make this work. So to wrap up, I hope.
Question on the last slide.
Sure.
Okay, so you talked about how in photomultiplier tubes, how the magnetic field can cause problems. And yet we also need the magnetic field to measure the momentum of the particles. So what is there some kind of compromise that's done between I mean, do we make some kind of compromise where we have a reasonably good magnetic field and a reasonably good photomultiplier tubes?
Yeah, that's exactly what happens. So I mean, the way you can get rid of, let's say, the perturbations of this magnetic field is, of course, by miniaturizing the entire device. That's exactly what silicon photomultipliers aim to do. Okay, but of course that becomes sort of a knob, right? It goes up to a certain level and then it still breaks down. But at the moment lives on or about 2 Tesla. So indeed, you can just use them in up to 2 Tesla magnetic fields. If you take something like that TPC over there, that's not so much about the size of the magnetic fields, it is about the uniformity of the magnetic fields, which is a very different problem.
Okay.
So all of that deeply goes into experimental design, yeah.
Okay. Well, I come from the CMS experiment, which has a magnetic field between 3.8 and 4 Tesla.
Yes.
And yet both our EM calorimeter and our hadronic calorimeter are both within the solenoid.
And you're probably very well shielded on your readout.
Okay.
And that's the other way, right? I mean, you basically need to prevent your local magnetic fields from
Okay.
penetrating.
Okay. Interesting.
What's the alternative?
I can't think of one.
Okay. Okay. What I hope to have shown you is that indeed there are good reasons why an EIC experiment has this sunrise shape in the end, why you need this to the rapidity acceptance region. What I've maybe not discussed so much is that one of the distinguishing features of this type of experiment compared to indeed an experiment like CFNS or Atlas is its longitudinal size. It's very compact, comes with the additional challenges indeed of integration. And it's also such that the combination with calorimeter and PID typically taking a fair bit of space, actually drives the need for a very compact tracking subsystem. I've not discussed this very far forward detection methods for breakout products, also not auxiliary measurements like, let's say, a lepton polarimeter or luminosity measurement. So with that, let me just wrap up.
Questions or comments?
I mean, in mathematics, when I write rapidity, it's a real variable which go from infinity to plus infinity, how you get 4? You just from the data from the energy of AIC, is your rapidity go from -4 to 4, how you get 4?
It's where the acceptance of the detector cuts off. It is not where the physics cuts off.
Okay, sure.
Right, so if you think in terms of a beam pipe, you always have a minimum angle that you can achieve. And that has nothing to do with, let's say, the beam rapidity of the beam itself. It is the geometrical constraint imposed by the beam pipe ultimately.
Thanks.
So it's a different beast. Right? It's not a physics quantity, it's an acceptance quantity.